Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad Umar bin Muhammad Yusuf, and today I would like to present my undergraduate project, which is a simulation of two-stage refrigeration cycle with flat chamber. And this project is supervised by Dr. Muhammad Yusuf bin Sunawi. Next, we go to the table of content, which is consist of 5 parts. The first part is introduction. The second part is literature review, and the third part is methodology, and the next part is result and discussion. Last and but not least is conclusion. We go to the introduction background study. We know as refrigerator are devices that produce refrigeration. It also known as cyclic device. The objective of this device is to maintain the refrigerated space as low temperature. To calculate this, we can calculate this performance of this device by using COP equation, which is COP equal to QL divided by Q net input. Next, we go to problem statement. The first problem statement is manual method is slow and taking time. The second one have higher percentage of error by doing manual calculation. Next, we go to objective and scope. For this objective, the first one to develop computerized simulation of two-stage refrigeration cycle with flat chamber. Next, using the C program to simulate the problem. We go to scope. The first one, steady state analysis of two-stage refrigeration cycle with a flat chamber. The working fluid for this simulation is refrigerant R134A. Next, we go to the literature review, which is single stage. This stage operates between two pressure limits, which is pressure condenser and pressure evaporator. It consists of 4 stages under which refrigerants circulate continuously. The system are adequate as long as temperature lift is small and not practical for application where the temperature lift high. Next is two stage. This stage consists of 2 cycles that are connected to flat chamber. It improves heat transfer characteristic by using flat chamber. It also increases the COP compared to the single stage. Next, we go to the computerized simulation. This computerized simulation uses equation developed by Cleland and refer to the refrigerant thermodynamic property equation by Chen and Hansenden. From these 3 tables, we can see the difference or the percentage error is less than 0.1% with the source data, which is considered accurate. Next, we go to the part 3, which is methodology. This part I summarized into 4 stages. The first stage is flowchart. We make a flowchart for step and process solving. Next, equation. We're using Cleland regression equation. Next, analyze. We set up case study by changing the parameter using C program. Next, result. We set up table and plot the graph that compare which one is the best or the suitable performance. Next, we go to the result and discussion. To study the case, we need to set a base parameter as a reference. This consists of 6 parameters, which is evaporator pressure. I had set into 244 kilopascal. Next, intermediate pressure I had set into 570 kilopascal. Next, condenser pressure I had set it into 1160 kilopascal. Next, superheating I had set into 0 degrees Celsius. Next, subcooling I had set into 0 degrees Celsius. Last and but not least, I had set compressor isotropic efficiency into 1. Next, we're going to the first case study, which is effect of superheating at evaporator outlet. From this table, we can see that the value of superheating is increased from 0 to 15 degrees Celsius. This table also shows us the value or the result of the output of this case study. Next, we go to the result of this case study, which is the first graph. The graph shows us the superheating versus refrigerating effects. When we increase the superheating, the refrigerating effect also increases. Next, we go to the second graph, which is the superheating versus total work compressor. As we increase the superheating, the total work compressor increases. This is due to the low pressure compressor and high pressure compressor is increases. Next, we go to the third graph, which is superheating versus coefficient of performance. As we increase the superheating at evaporator outlet, the COP also increases. Next, we go to the last graph, which is the superheating versus fraction of refrigerant that evaporate. As we increase the superheating from 0 to 15 degrees Celsius, the fraction of refrigerant that evaporate is constant, which is remain same value. That means we can see that the superheating does not bring affecting towards to the fraction of refrigerant evaporate. Next, we go to the second case study, which is effect of the subcooling at condenser outlet. From this table, the parameter that I change is subcooling, and the value that I change is 0 to 5, 5 to 10, and 10 to 15 degrees Celsius. And this table shows us the value or the result output of this case study. Next, we go to the result of the case study. The first graph shows us the subcooling versus refrigerating effect. As we increase the subcooling, the refrigerating effect also increases. Next, we go to the second graph, which is the subcooling versus total work compressor. As we increase the subcooling, the total work compressor increase. This is because of the low pressure and high pressure compressor is increases. Next, we go to the third graph of this case study. The graph shows us the subcooling versus coefficient of performance. As we increase the subcooling, the COP also increases. Next, we go to the last graph of this case study when the graph shows the subcooling versus fraction of refrigerant evaporate. As we increase the subcooling from 0 to 15 degrees Celsius, the fraction of refrigerant evaporate is decreases. Next, we go to the third case study, which is effect of compressor isotropy efficiency. From the graph shows the value of compressor isotropy efficiency have been increases from 0.6 to 0.9, and this table shows the result of output of this case study. Next, we go to the result of this case study. The first graph shows the isotropy efficiency versus refrigerating effect. As we increase the isotropy efficiency, the refrigerating effect is constant, which is maintained at the same value. And this shows us the isotropy efficiency does not bring affecting on the refrigerating effect. Next, we go to the second graph, which is isotropy versus total work compressor. As we see from the graph, the blue line indicate the total work compressor, the gray line indicate the high pressure compressor, and the orange line indicate low pressure compressor. So, the low pressure and high pressure compressor is decreases will be resulting in the total work compressor also decreases. Next, we go to the third graph, which is isotropy efficiency versus coefficient of performance. As we increase the isotropy efficiency from 0.6 to 0.9, the coefficient of performance is increases. This is due to the combination effect, which is the refrigerating effect is remain constant and the total work compressor is decreases. Next, we go to the last graph, which is isotrophic efficiency versus fraction of refrigerant evaporate. As we increase the isotrophic efficiency, the fraction of refrigerant evaporate constant, which is remain at the same value. Next, we move into the fourth case study, which is effect of intermediate pressure. From this table, the intermediate pressure value has been increased from 300 kilopascal to 1000 kilopascal. And this table also shows us the result of output of this effect. Next, we go to the first graph of this effect, which is intermediate pressure versus refrigerating effect. As we increase the intermediate pressure, the refrigerating effect increases until it reaches maximum point, which is 134.1172 meter cube per kg, then start decreases. We move to the second graph, which is intermediate pressure versus total work compressor. As we increase the intermediate pressure from 300 to 1000 kilopascal, total work compressor is decreases until it reaches minimum point, which is 29.08219 kilojoule per kg, then start decreases. Next, we go to the third graph, which is intermediate pressure versus coefficient of performance. As we increase the intermediate pressure, the coefficient of performance is increases until it reaches maximum point, which is 4.61175, and then start decreases. This is due to the combination effect of the refrigerating effect and total work compressor. And lastly, we go to the last graph, which is intermediate pressure versus fraction of refrigerant evaporate. As we increase the intermediate pressure from 300 to 1000 kilopascal, the fraction of refrigerant evaporate is decreases. Next, we go to the last part, which is conclusion. To get or to select the best performance of refrigerating cycle, we need to consider this factor. There are 5 factors that we need to consider, which is higher refrigerant effect, lower total work compressor, higher coefficient of performance, and lastly, lower refrigerant evaporate. That's all from me. Thank you for your attention.